after the talk. Yeah, that's all fine.
But let me go ahead and introduce you. So this is Meng Sun, a postdoc at UW-Madison. She is half theorist, half observer, but she's going to give a talk about orbiting binaries and edits she's making to the MESA stellar evolution code, correct? So we have a big group here that does stellar dynamics. Nice. So we're excited to see. All right, go ahead. Thank you.
All right, thanks, Angela. Hello, everyone. That's a great pleasure to be here. Well, I really wish I could be physically in Colorado at this time of the year. So far, like my only experience of Colorado is that I was transferred flight at Denver on my way to the Kitt Peak National Observatory. This background picture of the slide is the Wing telescope, which is my most frequent use telescope that associate with one of my other projects on binary evolution and blue stragglers. Just back to the main topic today, I'm going to talk about like how tides change the orbit of binaries and a new open source code to model stellar tides. My main collaborators on stellar tides are Rich Townsend from UW-Madison, Phil Ayres from the University of Virginia, Nevin Weinberg from University of Texas at Arlington, Guo Zhao from the University of Cambridge. All right. Okay. The talk will be in 3 parts. So in the first part, I'm going to talk about the basic physics and ideas in the theory of tides, and then I will talk about tides in closed binaries containing low mass or solar type stars and lake type stars. Then in the last part of the talk, I will introduce GYRE-tides, a new open source code to calculate the stellar response due to a companion in closed binaries, and some application of gyre as well, like in calculating the tidal response for intermediate and massive stars. Let's get started from the 3 effects for post-main sequence evolution in binaries. The first one is when the star increases its size during its RGB and AGB phase, its radius can like expand to over 1 AU. So like all the close-in planets are engulfed by the expanding star. The second effect is that instead of the star expansion by itself, the orbit decays by tides. Then the companion star will be merged with the primary star. The third case is that the tidal that during the heavy mass loss rate of the star in its late RGB or AGB phase, the star mass decreases dramatically, and which that makes the angular momentum per unit mass of the system increase. So like makes orbit expand. System like can be survived through this entire post-main sequence evolution for this case. The next is some like review of previous work on the 3 effects that I just mentioned. Here we have 2 orbital evolutionary plots for a 1 Jupiter mass companion on the left and a 1 Earth mass companion on the right. They all like orbiting around a 1 solar mass star. The y-axis is the system separation, and the x-axis are evolutionary time, like starting from the beginning of the AGB phase. And we can also see like the bottom curve, like the bottom black curves is the radius of the primary star itself, like during that's along with the thermal pulses. The red curves represent the case that the companion star is finally destroyed by the primary. If the initial and if the initial separation is big enough, so that's the black that's the black line tells us the story. So like so during the cases that the secondary star is survived and the orbit expands due to the heavy mass loss of the primary. The difference between the 2 plots is that for a Jupiter-sized planet, before merger, orbit shrinks because of tides. But for a 1 Earth mass companion, the tidal force is really weak, and the companion is just swallowed by the primary star due to this expansion of the star itself. And the tidal dissipation rate is negligible. We can also see like before the merger for the 1 Earth mass case, the system separation is nearly a constant. So previous people study how far out should be the planet so they can be survived over the entire post-main sequence evolution. I study the spiral-in process for all types of stars, where the binaries are in closer orbit and can be easily observed. Here, let me introduce the basic idea of how tides change the orbit and the spin of the star. The cartoon on this slide shows the model of Darwin's theory of tides. Here we use a big circle to represent the primary star, and that's the secondary. And let's assume the secondary rotate counterclockwise on this slide. The friction, the tidal friction, causes two bulges to lag behind the companion, and this lag angle is shown by this red dotted line. To simplify this case, like we use 2-point masses to represent the two tidal bulges. And we can also see the tidal bulge at close side and at the further side will generate forces pointing to two different directions. And the combination of the force can produce a torque that can slow down the motion of the secondary. This is like under the assumption that the primary star is a really slow rotator. In another case, if the primary star is like rotate faster than the orbital motion of the secondary, the system will expand, just like the Earth, Moon, and Jupiter Io system. The orbital decay rate for Darwin's theory of tides is in this formula on the right. The rate of change in separation, like A dot, is very sensitive to the radius of the star. Another interesting term I would like to mention is the last one, this one. Capital omega is the star spin rate, and the lowercase n is the orbital frequency. For the perfectly synchronization case, where the star spin equals to the orbital frequency, that makes dot A equals to 0, which means no tidal dissipation, like for perfectly synchronization case. For a fast rotator, where the omega, like the star spin omega, is greater than n, that makes dot A positive. That means the star expand, sorry, the system expand. People, in old works, like people treat this lag angle, like tau lag, as a constant or free parameter, which is calibrated by observation. While this approach usually underestimates the circularization rate of tides and overestimate the orbital shrinking rate. My model in calculating the tidal effect for all type of star do not take this parameterized equation. Like we calculate this lag angle or this term like case by case. All right, here I would like to mention a little bit about like the people working on tides and working on astroseismology, the bridge between them. Astroseismology refers to the self-excited mode inside the star. It can be analogous to like simple harmonic oscillator. The theory of tides just study the forced oscillators. Here I'm going to show the physics of the tidal flow and how do we solve the tidally driven wave equation. So we simply add an extra force to the gravitational, that is the gravitational forcing term in the fluid equation of stellar oscillation. The solution is solved numerically and can be considered as the sum of the sum of the long wavelength component and the short wavelength solution. The long wavelength solution is the equilibrium tide, which is the non-resonant fluid motion arising as a response to the time-varying gravitational potential of the companion. A good example is just the tidal bulges on Earth, like caused by the moon. That's all like equilibrium tide. The short wavelength solution is called the dynamical tide. It is the resonant excitation of an internal gravity wave. In astroseismology, we also call them SG mode. The plot on the top left indicates the structure of our example star. It has a radiative core and have a convective surface near here. The bottom plot gives the radial displacement perturbation of the wave as a function of radius through the star. It shows that near the surface, the solution is dominated by the equilibrium tide And we can see like this tiny part, like this no oscillatory feature, that's the equilibrium tide. And in the radiative core, and we see like very obvious like oscillatory feature. That is the solution. That means the solution is dominated by the dynamical tide. After talking about the mode excitation by the secondary object in the binary, then let me introduce like the mode damping physics. The first one is the convective damping, where the equilibrium tide are usually damped by the interaction with the turbulent eddies in the stellar convection zones. The equilibrium tide can create some like horizontal motion near the surface of the star. So let's assume like we have two fluid layers. The top one like moves towards right and the lower layer moves towards left. If we have a test molecule in the lower layer and it moves upward, it carries the momentum towards left. So it will decrease the momentum when it moves to the upper layer. During this process, there's can be a shear force can be generated, and we need this, and we need a molecular viscosity to calculate this shear force. The viscosity like has a same unit of the diffusion coefficient, so we need a length and need a velocity to get the molecular viscosity. The characteristic length for this molecular motion is just a mean free path. And we use that to multiply the thermal velocity of the molecule to calculate this molecular viscosity. Instead of molecule, there are large eddies like in between the hot and cold layers in the stellar convection zone and can slow down the relative motion between the different layers. The friction force will generate heat, then change the orbit and the spin energy of the star. To calculate this force and the tidal dissipation rate, we still need to choose a proper viscosity. The turbulent viscosity is the eddy's length times the eddy velocity, and the size of the eddy is much greater than the mean free path of the molecular. So, like in calculating the turbulent, so in calculating the tidal dissipation for the equilibrium tide, turbulent viscosity is much important than the molecular viscosity for the tidal dissipation calculations. All right, the second like damping mechanism, nonlinear damping. Let me try to use the water wave to explain this process better. So ocean like is shallower near the shore, and we can also see like water, the water like in like far away from the shore, they are sort of quiet, and when it propagates near the shore, it increases its wave amplitude. When the wave amplitude, like the wave height is comparable or bigger than its wavelength, the water wave will break near the shore. So back to tides. The wave-like response, dynamical tide, damped via the nonlinear damping near the center of the star, just similar to the water wave damped at the shore. The gravity wave steepens towards the center of the star, and its radial displacement perturbation is proportional to 1/r². R is the radius of the star. So like for keeping a constant energy through the core. During the propagation of the wave, the propagation of the wave like moving inward, the wave amplitude increases dramatically. And when this wave amplitude is greater than the wavelength, the dynamical tide can be damped near the center. And the wave energy can convert to heat during this process. Now let's assume a star like has a convective core, like in this region, like from radius from radius equals to 0 to radius equals to 0.1 r star. So instead of the mode damping at r equals to like 0.1 r star, the wave amplitude at here is actually like smaller than its wavelength. So instead of the wave break, the wave will reflect and form a standing wave. During this process, there is no energy transfer between the wave and the background star. So that means like whether the nonlinear damping works or not depends on the stellar structure. So only star with a radiative core, for example, like the low mass main sequence stars or late type RGB and AGB stars, it allows the dynamical tide to reach the center and damp there, grows a big amplitude and efficiently breaks. But starts with a convective core, the nonlinear damping is not that important. The third damping effect is the radiative damping, which is very, very important in massive stars. The wave-like response creates some compressed and decompressed region in stars, resulting hot and cold cells next to each other. And the heat flow can moves from the hot to cold cells. The heat diffused distance in time p is the square root of the heat diffusion coefficient multiplied by p. And if this heat diffused distance is greater than the wavelength, the wave will be strongly damped by radiative damping. All right, the top right figure shows the radial displacement as a function of radius. This is an example of a weakly damped low-order gravity wave. The adiabatic response is in the black dashed line. The non-adiabatic response is in blue, and the equilibrium tide response is in red dashed line. So the adiabatic response is more like an ideal case, and non-adiabatic calculation is more close to reality. So if we, for this case, if we force the star near the natural frequency of the low order G mode, the mode can be excited and but weakly damped. So the non-adiabatic solution should be very close to the adiabatic solution. So we can see the black and blue curves overlap each other. The bottom plot gives an example of how radiative diffusion cancels the wave-like response. So if we hit the star with a much lower frequency where a high order internal gravity wave should be excited, however, the radiative diffusion is able to damp this mode, making the non-adiabatic stellar response in blue that very close to the equilibrium tidal response in red. So yeah, so there's no oscillatory feature anymore. All right, here I'm just trying to use a table to summarize those keywords in the theory of tides. There are two main classes of tides, the equilibrium tide and the dynamical tide. They all generated by the time-varying gravitational potential of the companion in closed binaries or exoplanet systems. The equilibrium tide refers to non-resonant fluid motion with damping caused by the turbulent eddies from the stellar convection zone. The dynamical tide is the resonant excitation of the internal gravity wave and their subsequent damping by nonlinear fluid process or thermal diffusion. The dynamical tide has some other subcategory based on their restoring force of the excited wave. The internal gravity wave is restored by gravity, and some other type, for example, inertial waves, is restored by Coriolis force, and is only important in fast rotating stars, as most of the stars that I studies are kind of slow rotating stars. So in my calculations, I ignore the inertial waves. In the next part, I will introduce the main result from my calculation. For example, our calculation find that dynamical tide dominates for close separations, and the equilibrium tide dominates for relatively wider separations in binaries. Okay, the first application of my calculation is to get the orbital decay rate for the WASP-12 system. This system is so interesting because this is one of the shortest period giant planets. The WASP-12b is a hot Jupiter with an orbital period of only 1.1 days. By 13 years of follow-up observations, many groups confirm that this system is decaying with a time scale of roughly 3 million years. From transit, we also have the star mean density measured, and we also get the effective temperature from the spectroscopy. In order to fit the measured star properties, either a 1.2 solar mass subgiant or a 1.3 solar mass main sequence star works. I'm going to show how tides help us to break this degeneracy in choosing a proper stellar model for this system. Okay, because this system is so close, so the dynamical tide is the dominant tidal dissipation rate. In this work, the dynamical tide energy dissipation rate is computed from stellar models by solving the wave equations and apply the appropriate boundary conditions for an inward going traveling wave in the stellar radiative zone. Then we convert this wave energy dissipation rate to the orbital shrinking rate for this already circularized orbit. After checking all the stellar models that satisfy the observed values like mean density and effective temperature and other like measure, for example, like maybe the color, yeah, and something else. The result gives the orbital decay rate for like that varies from like 1 to 5 million year, which is exactly the same order of magnitude with the observation. That's good, like theory works. One important requirement is that the host star, the primary star in this system must be a subgiant with a radiative core, so the dynamical tide can propagate near the center and can nonlinearly damp there. The 1.3 solar mass main sequence star solution, like with a convective core, can explain the orbital, like the observed decay time, as the dynamical tide can't damp, or can propagate through the center and cannot be damped via nonlinear damping. So like it won't play an important role. Dynamical tide won't play an important role in shrinking the orbit for this like 1.3 solar mass model. So yeah, so this is how our work helped to constrain like the primary star parameter. It should be a 1.2 subgiant model instead of a 1.3 main sequence model. Okay, after talking about the specific case of the WASP-12 system, here is a more general case, the apogee survey. Apogee binaries are ideal sources to study tides because the first point is that it contains all type of stars, like varies from dwarfs to giants. And among those observed like binaries, there are about 180 systems that containing a red giant star at different stages. The companion masses like also like varies from planet to brown dwarf to stars, and they are in a wide range of the orbital period. So like which provide us a good lab to help us tidal theory. The orbital period like is getting by the radial velocity measurement on the primary star spectrum. The question is like, are those missing binaries, or the missing close binaries in the red squared region is due to tides? We try to answer this question, yeah, in the following slides. All right, in this more general case, we consider like both equilibrium and the dynamical tide in shrinking those near circularized orbit. The total energy is conserved, and so we can tap the orbital energy and put it into the spin energy and heat. The heating energy dissipation rate then can convert to the orbital decay rate. Here is the result, like showing the orbital evolution for a 1 solar mass star and a 10 Jupiter mass companion with different initial separations as 0.05, 0.13, and 0.2 AU. In the top figure, the y-axis gives the distance between the two objects, and the x-axis gives the log g from the main sequence phase to the red giant phase. When the tidal dissipation rate is really big, the orbit will shrink within a really fast rate. And we can also see there's a black solid line that indicates the star radius. So when the system like separation equals to the star radius, that means the two objects merge. System with close orbit and shrinks at early stage, and if we have a companion like with a wider orbit, it can like have a longer life and then can be engulfed by the star during the RGB phase. The bottom figure like gives the tidal dissipation rate contributed by the equilibrium tide in solid lines and the dynamical tide dissipation in dashed lines. In early or close orbit situation, like for somewhere here, dynamical tide dominates the tidal dissipation rate. And in the primary star's late phase, or where the star builds a big surface convective zone for that case, and the wider orbit situation, the equilibrium tide wins. And those three fiducial cases are actually all like destroyed by the equilibrium tide. Okay, from our calculation, we can also like define a critical semi-major axis, a crit, where is the age-dependent critical separation. For a given log G, it corresponds to a semi-major axis that beyond this separation, the system is tidally stable with no significant orbital decay. But within this separation, the system will be destroyed by tides rapidly and might be detectable by observation. Here we also like, and we also like shouldn't expect like there are many systems like that are smaller than a crit, because the time scale of the orbital shrinking is way smaller than the age of the system. The plot shows, the plot gives a numerical calculated like a crit lines for 3 companion masses, like varies from 1 to 10 Jupiter mass up to like 0.1 solar mass. All the apogee binaries containing a primary star around 1 solar mass are shown as open circles, and the size of the circles gives the observed companion masses. And we can see most of the apogee systems are above the a crit line, so they are tidally stable as we expected. Then we apply the same result for like a crit to the exoplanet system, where hot Jupiters orbiting around solar type stars. This time seems not that ideal because we see like so many systems. By the way, can you guys see my cursor?
Yes, we can.
Okay, great. Yeah, so at here we see like many exoplanet systems are below the a crit. That means like the orbital decay rate for those systems should be very rapid, and we shouldn't discover like many of them. For a quick in order to like explain this disagreement between observation and theory, so like we do a quick estimation, like in another calculation, that we suppressed dynamical tide in shrinking the orbit. So there's another like new a crit line in the dash blue line, represent a dash blue. That's the calculation result for the a crit, like if we do not take into account about the dynamical tide. So that makes most of the system like well above the a crit. So recall that when I introduced the nonlinear damping in the dynamical tide, there is almost no tidal dissipation for the dynamical tide when the star has a convective core. So in another word, dynamical tide might be suppressed for stars has a convective core. In the right plot, is actually a zoom in version of the left plot somewhere, yeah, about this zone. So I added more a crit lines for stellar models, varies from 1 to 1.5 solar mass. And we can see like the a crit lines is quite different in the main sequence phase, like just by increasing the stellar mass, like with only 0.1 solar mass. So there are also like uncertainties in log G and the mass measurement of the star. So let me use an example just to explain this problem in a more detail. Like let's say we discover a 1.1 solar mass star with a planet near A equals to 0.3 AU and log G equals to 4.2. Yeah, somewhere here. The system is below a crit, like compared with the 1.1 a crit line. But in reality, if the star is actually a 1.2 solar mass star, so we actually need to compare like with the 1.2 like solar mass a crit lines. So our result, like our conclusion is that the uncertainty in measuring the star mass may explain the disagreement between the theory and observation. Okay, another application of this work is to help with finding system that might have detectable p dot, the rate of change in orbital period. And although we shouldn't expect too many systems are well below the critical similarity axis, but like 1 out of 100 occurrence rate should be okay. On this plot, there are 4 newly discovered test systems, which are displayed with red stars. The shallow like red stars are like that means like the system are still in the process to get the star properties and the orbital parameters. Here I would like to mention this system, like TIC 2300, which is like way below the equate line. This system like is discovered by my collaborator, Sam Grambland, who is an expert in searching exoplanet around lake-type stars. This is an exoplanet system with a 1.2 solar mass primary, early RGB star. The companion star is a 2 Jupiter mass planet, and the orbital period is less than 5 days. So my preliminary result shows that the orbital decay rate of this system is around 10 million years. So in the follow-up observations, the rate of change in orbital period might be detectable. Okay, in the very last part of the talk, let me advise a new functionality in GYRE, which is an open source stellar oscillation code. Given an input stellar model, GYRE calculates its free oscillation frequencies and eigenfunctions. With a new development version of the code known as GYRE-tides, we can also like calculate the interior perturbations in a star caused by the gravitational field of a companion, which means that GYRE can model tidally forced oscillations. Like I mentioned, like at the beginning of the talk, the standard approach of the simulation, the standard approach to simulating tides involves parameterized equation that approximate how tides modify the orbit. GYRE-tides doesn't suffer these limitations because it undertakes a full numerical solution of tidal equations without any approximation. Therefore, it can better help us to analyze and interpret observations of closed binaries. Using Kepler observations, Thompson et al. Discovered a new class of hot beat stars. This name comes from their periodic flux variations feature a short pulse in the periodic light curve. And it looks like an electrocardiography. The middle biggest pulse is contributed from the tidal distortion of stars in an eccentric binary system near the periastron. And the tidally excited oscillations can also be seen, where the small pulses are from the dynamical tide. Just as cardiologists can diagnose the health of human being by monitor their heartbeat rhythm, we can also place constraints on interior structure of these stars and their binary evolution through the carefully study of tides. The Kepler mission found about 170 heartbeat stars, and most of them are A to F type stars, which means they are intermediate mass. While this is actually an observation bias because Kepler observes so few O and B type stars, but other space and ground-based mission such as Bright, TESS, Assassin report the heartbeat feature also can be found in massive O and B type stars, up to 30 solar masses. Now let me highlight 2 beautiful results from GYRE-tides in modeled heartbeat star KOI-54. This system is a face-on Kepler binary system in an orbit of 42 days. The 2 stars have similar masses. They are 2.32 and 2.38 A stars. The system is highly eccentric with an eccentricity of 0.8. Burkhardt 2012 provide an outstanding work for us to check the surface response result from GYRE, and both of the work are solving the inhomogeneous wave equation applied with radiative diffusion. The figure gives the radial displacement perturbation and flux perturbation as a function of forcing frequency by a fixed strength potential. And our results are in a very good agreement with Burkhardt 2012. At low frequency and at low forcing frequency on the left of the plot, the solution is dominated by the equilibrium tide, where the non-resonant tidal, which is the non-resonant tidal response. And in the left middle of the plot, where the orbital harmonic K varies from 15 to 30, that's the solution here is represent the strong it showed the example of radiative damping in reducing the internal gravity wave amplitude near the surface. So that's caused by the radiative damping lower the wave amplitude near the surface. All right, and seen from the right of the figure, those are there are many big spikes. They are at high frequency, high forcing frequency range. The spikes are resonant excitation of the weakly damped gravity modes. All right, another GYRE-tides can also calculate the rate of change in orbital elements for binaries containing a massive star. This figure plots the rate of change in semi-major axis and the eccentricity as a function of orbital period for an eccentric 1.4 neutron star racing tides on a 5 solar mass main sequence primary. Generally, those time scales are smaller for small orbital period and larger for long orbital period. That's due to the strong dependence of tidal strengths on orbital separation. However, we can still see many spikes where the time scale becomes very short. Those correspond to high amplitude dynamical tide arising from the resonance with the primary stars, dense forest of the standing gravity waves. One additional point I would like to mention is that for making this plot, I just run GYRE-tides on my 6-core personal PC, my personal laptop. Our code is a couple of order magnitude faster than the caffeine code. That is the only other public available forced oscillation code. And the current version of GYRE-tides considered radiative damping, only considered radiative damping, but no convection damping and no nonlinear damping. It still works well for star have a convective core and a radiative envelope. For low mass star, we need to be careful in using GYRE-tides because we may underestimate the rate of change in those orbital parameters because we do not, so far at this development stage, we do not consider nonlinear damping and convective damping that are important in low mass stars. Okay, to summarize the result, my own code of calculating the tidal response can explain the orbital decay rate for WOSPO-12 system by dynamical tide, and we can also explain the lack of closed binaries in the apogee survey by tides. Then I begin to study tides in intermediate and massive stars, and I also help Rich, the main developer of GYRE-tides, to develop this open source code GYRE in calculate the forced oscillations. Instead of using the parameterized equation to see how tides modify an orbit, GYRE-tides can undertake a full numerical solutions of the tidal equation and can predict the orbital shrinking, circularization, and synchronization rates. The code will be available for public soon, just as MESA and GYRE allowed a much larger community to carry out stellar structure calculations. We expect GYRE-tides will allow a more non-spatialists to carry out state-of-art calculations of tidal friction in binaries containing massive stars. All right, I will just stop at here and take questions.
Thank you. Let's thank our speaker. Where's the button? Can you elaborate on, I have a question. I'm gonna go first, but thank you. So in the apogee data, we're missing these closed binaries, and your suggestion is that the tides cause the binaries to
Yeah.
like just spiral in. Is
Mm-hmm.
there a time scale for that? Like your average one solar mass star, how quickly are they going to spiral in?
Yeah, I can say, good question. I can say like, so like the lifetime, like the whole lifetime of a solar type, like or binary containing a solar type star should be like in an order of magnitude of 10 gig a year, or like or 12 gig a year. 10 gig a year might be just the main sequence lifetime. So like so I can say the time scale of the orbital shrinking compared with the time scale of its lifetime might be like 0.0 point, the ratio between them should be 0.01. So like in an order of like maybe million year, or yeah, or like maybe like 1 to 100 million year. Yeah, that's the, I know it's a big range, but like
Yeah,
still like
that's
quite
fast
smaller
though.
than, yeah,
Yeah.
it's fast.
Mhm. Does anybody else have a question? There's one in the chat. Let me see.
Oh, sure. Yeah, could you please, because I'm screen
Yeah, I
sharing, so I
can.
cannot, yeah, read the
It
chat.
says, I've been looking for something like, oh, did you call it GYRE-tides? Now that I'm reading it, GYRE-tides for a while.
Oh,
Does the
GYRE-tides. Yeah,
GYRE-tides?
yeah,
Wow.
gyre.
Does the
That's
code
fine.
allow for nonlinear mode coupling? Very
No,
specific question.
not at that stage. Like the nonlinear damping or like mode coupling or three mode coupling. Yeah, still in the further development. Like the next step of our work is actually like first we need to consider at an actual term, like the convective damping term, like in the wave equation, and also the nonlinear like damping term, and then like so make the code like much like be applicable for like more solar type star. I know like the exoplanet community are looking forward that, because like most of the exoplanet, like they discovered orbiting around solar like stars. Yeah, so but yeah, that's on our plan. So far we don't calculate like the three mode couplings. Like yeah, it is that's really challenge, like for numerical calculation. It is really hard.
Zach, do you want to ask your question?
Sure. Thank you for this wonderful talk. This was awesome.
Thank you.
Uh, I love your experiments of like figuring out the mass of the star based on the tidal decay of the planet, or like what possible scenarios here. And you showed these nice population plots of all of these planets compared to these curves of what's the critical A that's for different masses.
I mean this one?
Yeah. And
right.
So if I understand correctly, you said something about that, like you think most of the things that are over the lines right now are just bad stellar parameters.
I think
But
so.
I was wondering, are any of those also just like good candidates to look for p dots, to look for period decays?
I'm not an expert like of like picking out, like I don't know like which system has a better measure like orbital like parameters or the star parameters. But like my colleague like working at the American Natural History Museum, like he gave me some interesting like test system. Yeah, just like this one. So like
yeah, the test systems look wacky.
yeah, and we actually like, expect like test found more of these kind of systems. So like this one, like we calculate like the like the star model. I don't have a very precise star that's ongoing. Like I didn't have a very precise star model. Just want to like have a roughly estimate on this system, so that have an orbital decay rate of 10 million year. I think that can be kind of like detectable, because like WASP-12 has a orbital decay time scale for like 3 MYR. So I suppose like once p dot or p over p dot in a range from 1 to 10 million year, it can be detectable, or it can be detected. This one I would also like to mention like Kepler 91b, because like Kepler like is older, like, and we have more follow-up like observations. I believe like this system is also like well constrained by like the orbital parameters or the star parameters are well defined or well measured. And yeah, and once I found this system are quite below the accurate, I also go to see the light curve of this system, and we see like other than like the planet, like racing tides on the star, the planet itself is like sort of ellipsoidal. It's also like it's in the second like phase that tides on planet is also important because they are so close, like in this late type star. So yeah, so I'm hoping that like this plot can also help observers to at least give them a first judge of whether the system might have big P dot.
Cool. Yeah, thank you. This is awesome because there is like one of the things is that WASP 12 was like one of the first transiting planets found. So it's just that we've been looking at it for 15 years or whatever it is.
Yeah, it's long. It's a long time. Yeah, I know
so
like
the
so far they are like about still like less than 10 system or 10 exoplanet system that have been confirmed with a P dot. Yeah, not too much, quite yeah, only yeah, it's a small like population compared with all the like system we found, but less than 10 of them like have been get the P dot.
Totally. Cool. Thank you so much.
Sure. Thanks for the question and comments.
Are there any other questions?
I had one more question, unless someone else wants to. Maybe I'll turn on my video. Yeah, so I'm wondering, are tides ever important for pre-main sequence evolution? So you discussed like quite a few different evolutionary stages.
Yeah.
I'm wondering if it could also be important at very early stages.
I understand. Yeah, that's out of my research, but like this is very interesting. Like all my simulations start from the zero-age main sequence of the star. So my first intuition, like to answer that question, might be not quite important, like tides in such a puffy like stars, and there's it requires like more physics to study tides because like PMS or pre-main sequence star might rotate really fast. So like this time we can't ignore like the inertial wave or the Coriolis force like in the wave equation. So like if we not quite sure, like if we consider all the physics in, maybe not important, but maybe tidal dissipation rate is not quite important. But I never run a like simulation like thinking about like the fast stellar rotation. That might give a different answer, I think. If we ignore like all the rotation or some other mechanism like in the PMS phase, different answer.
Yeah. Okay, thanks. Yeah.
Yep.
Okay. All right, let's thank our speaker again. And thank you all for coming. This is a great one. I'll send you an email when it's up. Okay.
Oh, sure. Thanks.
Bye, everybody.
Oh, bye. Have a great weekend.
You too.